Hi, people. Welcome to Linear Algebra, Lecture 14, Spring Semester 2023, Keio University, Shonan Fujisawa campus. Let's get started. Give me just a second here. Let's pull up some slides. There we are. Share the screen with you. There we go. Hopefully. And roll them. All right. So today is lecture 14. We're going to talk about graph theory, Markov chains, and error correction. The graph theory is just a quick pickup from where we were the last couple of weeks. And then I'll show you how it connects to Markov chains and error correction. So this is lecture 14, and ta-da, that means end of the semester, last lecture. So thank you all for being with me. Thanks for doing the work and interacting in class, and hopefully learning something while you were at it. Graph theory we've talked about over the last couple of weeks, and we've shown a little bit about how it's related to linear algebra. Today we're going to extend that into a notion called Markov processes, which it turns out will actually be a little bit familiar because you've actually already done a little bit of it, even if you didn't necessarily realize that. Then we'll end with a discussion of error correction, which is how errors are actually handled in communication systems and computers. Today, we're actually not going to cover the quantum stuff, unfortunately, but if you're interested in that, ask me about it sometime. So first topic here, graph theory. We've already seen the adjacency matrix. On the right-hand side of the screen here, you've got a matrix with 6 nodes, A, B, C, D, E, F, which means we can describe it using what's called an adjacency matrix that happens to be, surprise, 6 by 6. Every entry in this adjacency matrix is either a 1 or a 0, and the 1s represent where nodes are connected, and the 0s represent where they're not. So for example, AD has a connection here. So in the D column of the matrix, you'll see that the entry in the A row is 1. That's because A and D are actually connected. As described this way, this is what we call row major form. For undirected graphs, it's actually not a big deal because it's actually symmetric. If you transpose this, you flip it about the diagonal axis, it's actually the same. But in directed graphs, that's not necessarily the case. So you'll see here that node B has an edge from node A, and node C has a hang on, let's see. Node A receives only from node A is connected only to B. Okay, yeah. Node B is connected to C and D. Okay, right. Yeah, this is right. If you look at the first row, that's the A row. A has a connection only to node B, and so only the entry in column B has a 1 in it, and all the others are zeros. B, on the other hand, connects to C and D. So in the second row, corresponding to our letter B, you'll see that the third and fourth entries in the matrix are actually 1. That's the entries for connections to C and D, or the directed edges there. C connects only to D, and so only the third row only has an entry in the fourth column, and D connects only to A, and so it has an entry only in the leftmost column. Let's look at some smaller graphs just to review a couple of things. Here up at the top, we've got the 3-node graph ABC. A is connected to both B and C, so the A row has entries in B and C. B is connected only to A, and C is connected to only A, and so you'll see that particular set of connections. If we talk about taking 2 steps on this graph, always having to follow an edge when we move, if we start at A, we can go ABA or ACA. If we start at B, we can go BAC. If we start at C, we can go CAB. That's about it, right? Also, and B, A, B, and C, A, C, right? So that gives us a total of 6 entries here, actually. What this tells us, if you look at the graph in the lower portion of the slide here, the upper left entry of that is 2. What does that mean? It means that there are actually 2 paths, 2 ways to start at node A, take exactly 2 steps, and wind up back at A. This is true for anything on the diagonal. And so B, there's only one way to do it. So for node B, you can go B, A, B, and that's the only way to start at B and end at B. This, it turns out, corresponds to the square of the adjacency matrix above. So to describe 2 steps on the matrix, all you have to do is you take the adjacency matrix and you multiply it by itself. That will tell you then how many possible paths there are to get from any node in the network to any other node in the network. For a bigger network like this, if we want to calculate how many paths there are between A and E that are exactly n steps long, the way we can do this is by taking the adjacency matrix A and taking the nth power of this. So what can we do with these kinds of graphs? Well, we can use them to model the relationships between objects, or people, perhaps. For example, we can use them to model computer networks, but one of the most interesting applications these days is modeling social graphs or social networks, like, say, Facebook or something. For example, if we want to calculate the diameter of a graph, we can do that too by figuring out how many time steps it takes us, how many powers of the matrix A we have to calculate in order to get to the state where every entry in the matrix is non-zero. That's an interesting way of actually calculating something. So if we talk about a social graph like Facebook, in fact, it has been said that the maximum degree of separation of any 2 people on the planet is 6. And we talked about this the other day. How many steps would it take me to get a letter from myself to President Biden if I had to give it to a person who then gave it to a person who then gave it to a person? This particular graph is actually from Facebook's own research, and what they've shown is that across their entire billion-person graph, that the average number of steps between 2 people is 3.57. And the maximum was, I think, actually under 7 or something. So, according to this general idea, with 7.5 billion people on the planet, if we built a social graph of all of the people on the planet and wrote out the adjacency matrix, if we took the 6th power of that matrix, every entry in that adjacency matrix would become non-zero. How amazing is that? It's just an incredible concept that we could connect everybody that quickly. All right, that's just a review of the things we talked about 2 weeks ago when we did this in person in class, and last time when we actually did hands-on exercises in class using the Jupyter notebooks. But I want to talk about another problem that we didn't get to last time, and this is a problem called graph isomorphism. The word isomorphism derives from a couple of Greek words, isos meaning equal and morphe meaning shape or form. And a graph isomorphism means that we can map all of the nodes or all of the names of nodes in one graph to names of the nodes in another graph, and the shape would be the same. The things that are connected to each other would be the same. So for example, here are the 2 graphs that you see on the screen. They're both 3-node graphs, and they look the same to a human eye, but if you look at the labels in them, one of them is labeled with A at the root at the top, and the other one is labeled with C at the root at the top. The graph isomorphism problem is to figure out, can we relabel all of the graphs in all of the nodes in one of our graphs and get another graph that's identical? So are the 2 graphs actually the same? The way we can do this in this case, if we take A and we rename it to C, and we take B and keep it to B, We take C and rename it to A, then you can turn the blue graph on the left to the yellow graph on the right. If we want to do this in the adjacency matrix, we've got a little bit more of a problem. It's starting to get a little bit more complicated here. So in fact, what we want to do is we want to swap the C and D rows and columns. In this case, for example, if we want to swap C and D, which takes a little bit of effort. This corresponds to, in linear algebra, a change of basis, where we're changing the order in which we care about particular terms in the matrix, or what are the basis vectors for our entire system. When we're talking about a discrete set of things, A, B, C, D, this can also be what we call a permutation. So, for example, the vector on the left there, 1, 3, 4, 7, can be turned into the vector 3, 4, 1, 7 by multiplying by some matrix P. And that P then would be the permutation matrix, and that would be this. So in this case, you see the first row is 0, 0, 1, 0. That takes the one entry in the vector 3, 4, 1, 7 and puts it in the topmost entry on the left there, and correspondingly from there. So P would be our permutation matrix there. Now, how can we determine if there's a graph isomorphism using this linear algebra this way? Well, if we take this, we can also get the full adjacency matrix for the graph using not just P, but also the transpose of P, and multiply it by the adjacency matrix, sandwich them around the adjacency matrix for our second graph. So you start with the adjacency matrix for the blue graph on the left and the adjacency matrix for the yellow graph on the right. And the question is, can you find a P and P transpose such that it makes this equation true? As it happens for this particular case, we've already seen sort of intuitively how to do it. The way in which you would do it is using this matrix that happens to be symmetric about the diagonal, and so the transpose is the same, where it's actually the anti-diagonal matrix here, and that would actually rename or permute your set of entries in the adjacency matrix and give you the full-on original adjacency matrix for the graph on the left. And so that would turn the yellow graph into the blue graph. Alternatively, if you had a different ordering, right? So if we had instead of having C as the root in this figure, if we had B in the root, instead the adjacency matrix would look like the one in the middle here, and the permutation, the P and the P transpose would look instead like you see here in the figure on the screen. One more concept we didn't get around to talking about over the last couple of weeks about graphs is actually a notion that we call connectivity. So we can check whether our graph is connected, whether or not all of the nodes actually have some path that connects them following the edges, by looking to see if there is some way to connect these two using the path counting mechanism we talked about before, where we're looking for non-zero entries in the nth power of the graph, or the nth power of the adjacency matrix. So question is, could you take this and actually write down the adjacency matrix for this graph, including all 6 nodes, and then multiply out powers of that adjacency matrix in a way that then would show you the number of paths between a pair of nodes, and would every entry in that nth power of the adjacency matrix wind up being non-zero? In this particular case, in the case of the graph here on the screen, you can see that E and F are connected to each other, but not to the larger graph A, B, C, D. So we would call these two separate subgraphs here, we would call them components of our larger graph. And so in this case, in fact, they're not connected. So if you write down the adjacency matrix, in this case, if you take any power of that adjacency matrix, A, you're never going to get a path that shows you how to connect E to A, because it just can't be done. Now, this is interesting when you switch from talking about undirected graphs to actually directed graphs, because as we've seen, the adjacency matrix for a directed graph isn't necessarily symmetric, and it shows a little bit more structure to it. In this particular case, it might be a little bit harder to see whether or not the nodes are actually connected. When we talk about a directed graph, we actually have a term that represents a stronger condition on the overall network. In this case, we'll call it the strongly connected condition. And the strongly connected condition means that on a directed graph, there is a path following the directed edges from every node to every other node. Now, looking at this, you can see that B is connected to D, but there's no way to get from D back to either B or anything else in that ABC triangle up there at the top. So you can start from A and you can get to B and you can get to D and you can get to E, but you can't get to C. If you look at the triangle at the top, there's no path that gets you from A to C. And from D, E, or F, there's no path that will take you to A. So this particular graph would not be strongly connected. So what can we do with these kinds of graphs? Well, you can write down a graph that describes the distances, or that describes a network, or that can be used to describe various aspects of a chess game or a chess program using undirected graphs. Using directed graphs, we have concepts we'll talk about a little bit more. We'll have Markov chain process, and you can talk about flow in an of electrons, or power, or electric current in an electrical circuit, or flow of water through a set of pipes. We can use a directed graph to model the evolution of a system, or we can use them to represent ultimately random walks. And this takes us to Markov chains. Markov chain is a probabilistic process with the discrete set of states. So we're not talking about something continuous here. We're talking about you are always in some particular state within a set of possible states. You can move from one state to another. The way you move from one state to another is by following an edge in this particular directed graph. So the example that's shown here on the screen, this is something I made up describing the transition probabilities at Markov University, let's call it. Let's say you have to spend 4 years at Markov University in order to actually graduate, and then once you graduate, you're going to go either to work or to graduate school. But it's also possible that you flunk out after your first year, that you actually leave the university, or that you voluntarily leave the university for some particular reason, because you get a good job offer or something like that. And that can be true at each of the 4 years, year 1, year 2, year 3, or year 4. And it's also possible that in each year that you fail to advance to the next year. So if you look at over there at year 1 on the left, these are just numbers I made up that have nothing to do with anything anywhere. The transition from first year to second year is 0.94. That means that there's a 94% probability that you're going to advance from being a first-year student to being a second-year student. You see the bigger, thicker arrow that curves back on itself? That's the probability that you stay in the same state. and that's labeled with 0.05. So it's a 5% probability that you're actually going to stay as a first-year student. And then as a first-year student, there's a 1% chance you're actually going to leave the university and get a job of some sort instead. But in our university, our fictitious university here, maybe year 2 is the tough one. So the transition, moving up or advancing from year 2 to year 3, the probability of that happening is only 0.77. It's only 77%. There's an 18% chance you're going to stay as a second-year student and repeat the second year, and a 5% chance that you're going to leave the university and take a job. Third year, you see 0.7 probability of going from third year to fourth year, and a 0.2 probability of excuse me, of staying as a third year, and then 0.1 probability of leaving and taking a job. So third year, maybe things got a little bit easier, but all the same, people are distracted with various things in their lives, and so probability of people not advancing to fourth year is actually sort of high. Then your fourth year, after 1 year as a fourth year student, there's a 15% probability you go to graduate school, in which case you're done. You leave our particular system. 15% chance you stay in the fourth year, and a 70% chance that you graduate and enter the workforce. All right. Each of these arrows represents a transition probability. This is a graph. I haven't drawn it using circles. I've drawn it using these rounded boxes, but it's the same thing. The other new notion that we've introduced here that we have so far avoided is what are called self edges or self loops. In this case, where you're not required to leave your current state. There's actually some probability you can stay in this particular state, and that's represented by one of these bigger self loops that are drawn on here. We can write down something like a transition matrix for this, and we'll call this the well, again, we'll call it the transition matrix. But this time, instead of having discrete 0 and 1 entries like we had in the adjacency matrix, instead what we're going to actually put into these entries inside this matrix, they're actually going to be the probability that you transition from one particular state to another. So here's a 3-node example, a simpler example. So if you're in A, in this example here, there is a 100% chance you're going to move to state C. We'll call each of these a state. If you start out in node B, there's a oh, sorry, I was looking at this wrong. So the each column represents where where you are going from, and then the row represents where you're going to. So going from A, there are actually 2 arrows going out from node A here. So we've written it out as there is a 50% probability of going to either B or C. So you see there are 2 arrows going out from there. So starting from A, looking down the A column, there's no probability that you stay in node A, but there's a 50% probability you go to B and a 50% probability you go to C. Sorry about that. I was looking at this backwards. Looking at node B, B is only connected to C. So if you look down the column C, or sorry, the column B, I'm going from B to A, 0 probability, B to B, 0 probability, B to C, 100 probability. And same thing from C. The only place you can go is A, and you always go. On the other hand, starting from any particular place, if we go 2 time steps instead, we can do the same thing as we did with counting the number of paths, or the path length in a particular graph. If you start at A, after 2 time steps, there's a 0.5 probability, or the 50% probability that you're going to come back to A. Now, how does that happen? Well, there was a 50% probability that you went from A to C. And once you're at C, there's a 100% probability that on the next time step, you'll come back to A. So earlier, we were counting the number of paths. In this case, what we're counting is the probability that after a certain number of steps, you will have gone from a particular node to another particular node. Starting from B, after 2 time steps, there's a 100% probability you're going to be at node A, because in the first time step, leaving from B, the only place you can go is C, and you're definitely going there with a probability of 100%. Going from C to A, there's definitely 100% probability you're going to do that. So after 2 time steps, the only thing you can do starting from B is to go BCA. On the other hand, starting from C, the first step, there's a 100% probability you're going to go to A, but then the second step, there's a 50% probability you'll go to B and a 50% probability you'll go to C. So you can see that in the right-hand table on this slide, and it's essentially, well, it's taking that transition matrix there on the left, the transition probability matrix on the left, and squaring it. 2 time steps takes us potentially probabilistically this many steps from one place to another. All right. One of the most important uses of Markov chains is what we call queuing theory. And let me show you a little bit about that. This is a screen capture of a set of notes that I've written here. Let me see. Hopefully they come up when I do this. Let's see. They did not. Where are they? Here we are. This set of notes, you can consider this to be optional. Normally, this is something I actually teach in the graduate school. Queuing theory. Markov chains wind up being strongly related to queuing theory. Queuing theory is what? Well, it's the mathematics describing how long you might have to wait at the bank if you go to the bank, or how long it takes you to get your food in a restaurant, or something of that nature. It's also, of course, critically important in computer networks, because in computer networks, you're receiving a packet from somebody, but you don't know when that packet's going to arrive. The arrival of that packet is what we call a random process. So when a packet arrives at a particular node in a computer network, we want to decide what to do with it. We want to decide whether to send that packet on to somebody else, but the processing of that packet has to wait its turn. If there are other packets that are already in the system that are waiting, then those packets are stored in what's called a buffer or a queue, and we want to know how long that queue is and what the average waiting time is. What's the average time it takes for us to actually do this? This figure here is actually a cartoon from the New Yorker magazine that I liked that really reminds me of queuing theory. It's a bunch of birds waiting their turn at a bird feeder. So when any given bird arrives at the bird feeder, it doesn't know before it gets there how many other birds are waiting. It might be nobody, or it might be a long line. And so this is exactly how queuing theory works. In this set of slides, or sorry, in this set of notes, you'll find this set of notes in the Sol system. They are there listed in a couple of places under files and also under lecture 14. These entries in the margins here, where it says pages 11 to 16, figures 2.1 to 2.3, these correspond to entries or to places you can find more about this in a book known commonly as Kleinrock. Professor Leonard Kleinrock is a professor at UCLA who was involved in the early development of the internet, as well as other things. He is the master of all things queuing theory. He wrote what's considered the standard book on the topic, although it's awfully expensive these days. But the Keio University library system, the media center, has copies of it, and so you can check it out from the library if you don't want to buy it. This set of notes covers roughly the first 102 pages of Kleinrock, just covering discrete systems, and there's not continuous stuff in this system. Doing the continuous versions of things would require calculus, which we're mostly not doing in this course. So this set of notes, like I said, queuing theory is often taught in graduate school rather than undergraduate. This first 100 pages or so of Kleinrock, there's nothing actually in it that's particularly super difficult mathematically. It's just that there are many other mathematical topics that you get taught in an undergraduate curriculum. And so we often don't get around to teaching queuing theory. But queuing theory tends to show up in graduate school curricula, in electrical engineering programs, or in some computer science programs, particularly ones that emphasize something like networking. All right, so what do we got? Here's a representation of a queue. You've got a waiting area, which is the queue itself, and you've got some service that you're applying. We're generally going to use these two terms, mu and lambda here. Lambda is the rate at which things for you to do arrive, whether that's packets or customers in a restaurant or whatever. Mu is the rate at which you finish their work and get them out of your system. If we analyze these sorts of systems, they will tell us, among other things, how fast a system we need, how fast a network or how fast a writer is, how fast a router is in the internet. We'll learn about the impact of parallel servers in the system, and even simple things like how much space do you actually have in your do you have to have in your waiting area, how big a buffer is actually required. If you study this carefully, you'll find that I think that queuing theory will actually change the way you think about computer systems. Let's see, how much of this do I really want to go through today? We can go into it in a fair amount of detail. This is a total of 13 pages here, but that includes actually some source code and also some requests for additional source code for this. If you send me additional source code, I will incorporate them. Let's go through this real quick. Let's see, where are we? Notation. We're going to use a thing called Kendall's notation, which we'll discuss in a minute. Before we get there, let's see. N of t will be the number of jobs in the system or in our that are either currently being worked on or waiting to being worked on at time t. This n bar, or sometimes w, is the average of the number of jobs in the system. Lambda is the arrival rate. That's the number of customers per second. Mu is the departure rate. Would be same units as lambda needs to be. Capital T, or sometimes capital L, is the average time spent in the system, also known as the system time. Two other things, which we actually won't use very much. Alpha of T is the number of customers who have arrived so far in the history of our system. Delta T is the number of customers who have departed from our system so far in the history of the system. And this little letter, this is not the English P, this is the Greek rho. Rho is the utilization of the system, or it's the fraction of the time that the system is actually busy. X is the service time or the processing time, for not including the waiting time, just the amount of time it takes to process this. And X bar is the average. For most cases, or for all the cases we're going to worry about here, X bar equals 1 over mu. So mu was our arrival, or was our departure rate, how long it takes to, or how often things tend to leave the system. So if an average of one customer or one job is completed every second, then the departure rate will be 1 per second, and X bar will be 1 second. Now, up here we said n is the number of jobs in the system. alpha is the number that have arrived, delta is the number that have left. So pretty obviously, n of t equals alpha of t minus delta of t. That tells you how many there are. All right. The most important result in queuing theory is a thing known as Little's result, which you might see written in one of two ways. You might see n bar equals lambda t or L equals lambda w. What it tells us is that the average number of people in the system is the rate at which people arrive multiplied by the average amount of time they spend in the system. So n bar here is the average number of people in the system. That's including both people who are waiting to be serviced and people who are being serviced. Lambda is the rate at which people arrive, and t is the amount of time that they spend in the system. It's the t here. So the average number of people in the system is the rate at which they arrive multiplied by the average amount of time they actually spend in the system. The remarkable thing that's about this is that this is completely independent of, well, what's written here, the arrival or service distribution. What does that mean? The arrival distribution is not just the average rate at which people arrive, but the actual pattern with which they arrive. Do they arrive at fixed intervals? Is it always exactly one person exactly once a minute? Or do they arrive at random? Or do they arrive in bunches? None of that matters for this particular result, for Little's result here. Same thing for the service distribution being the amount of time they actually spend in the system. Doesn't matter if they all take exactly the same amount of time in the system, or if the amount of time it takes you to deal with one particular customer is random, sometimes short and sometimes long. None of that matters to the completeness and accuracy of or to the validity of Little's result. All right. Let's talk about a Markov process. The Markov process is one in which the next state of the system depends only on the current state of the system. There's no deep history. There's nothing about where you were yesterday or where you were the day before. The only thing that matters when you make a decision about where to go next is where are you right now. Radioactive decay is one example of a Markov process. The probability that an atom will decay, it will emit a particle and will go through radioactive decay. The probability of that happening in the next second has nothing to do with how long it hasn't happened in the past. The only thing that matters is it has not yet decayed. In the next second, there is a fixed probability that it will decay. If we have a discrete state space, then we have a system that's known as a Markov chain. With a Markov chain, time can be either discrete or continuous, but the set of states is discrete, meaning, for example, with the atom can be either decayed or undecayed. It can't be halfway decayed or 90% decayed or something like that. It always either is or isn't. This being a Markov process, meaning that the next state depends only on the current state. Another word for that is that a Markov process is what we call memoryless. That's a term that just means that, again, the deep memory, what happened yesterday or the day before doesn't matter, only the current state. A continuous time Markov process will have an exponential distribution of states, while a discrete time process will have what's called a geometric distribution. if you ask Google Sensei for what the difference is between a geometric and an exponential distribution, you won't get a very helpful answer. You won't get something that's really sort of enlightening. But for our purpose, what it means is the geometric means that the function moves in discrete steps and with an exponent that's always an integer. But first off, let's talk about discrete time Markov processes. We're going to use a probability vector like we saw earlier when I was working with the slides. Except, well, we talked about the transition matrix, but we actually did not talk about the probability vector yet, did we? We didn't talk about the probability that you're in a particular state. Well, we're going to use a vector, which we'll call pi. And that will be our probability vector that says we're in a particular state. So if there are n possible states, then our vector pi has n possible entries in it, and pi sub I is the probability that the system is in state I. Then P will be our transition probability matrix, like the ones that we had back here in the slides like this. So transition matrix like this. For each time step, the only thing you need to know in order to calculate that is this transition matrix, transition probability matrix P, and the vector pi describing the current state. So we'll write, we will write the current state or the time at state t. We'll write that as pi, then with t as an exponent in parentheses, and so t of pi pi of t plus 1 equals pi of t times p. Pretty straightforward. This is a matrix, this is a vector, but this time so far this semester in most of our calculations we have done a times x, where a is the matrix and x is the vector, with the vector always being on the right. In this case, we're going to do left multiplication here, and so the vector is on the left, and then the matrix is on the right. The calculation process is exactly the same. One of the things we want to know when we are working with these kinds of systems, and we're talking about Markov process systems, we want to know about the equilibrium state, or the steady state of this. What we want to know is if we multiply out things using this equation, this pi t plus 1 equals pi of t times p, when does pi t1 pi of t plus 1 equal pi of t? When that happens, then the state has reached equilibrium. Does this sound familiar? It should. This is exactly like the rabbit population system, rabbit population set of equations we looked at back both in the very first lecture of the semester and again sometime after that, using the Georgia Tech Online Interactive Linear Algebra textbook. That's exactly what we want to find here. That should also tell you right away that if this pi corresponds to roughly to the population vector in that rabbit population example, what we're looking for here is we're looking for eigenvectors. We're looking for eigenvectors of the system such that pi of t times p equals pi of t, like this. And so pi steady state equals pi steady state times p. That's basically the definition of finding an eigenvector with an eigenvalue 1, which are the kinds of things we've already done. Let's take as an example Keio student Hanako Keio. She likes to spend her time in the 3 cities, Kyoto, Tokyo, and Osaka, and will represent those 3 cities in our state vector pi. Every day she stays in one of those cities, and then from that city she goes to, well, either the same city or one of the other cities, but she moves from city to city with some probability. we can write this out using a transition probability matrix like this P. And if these are three cities are Kyoto, Tokyo, and Osaka, then the first column represents the probability that she goes from Kyoto to another city. The second column represents the probability that she goes from Tokyo to another city. And then the third column represents the probability that she goes from Osaka to another city. So this matrix P here, the probability transition matrix, we can write this out as a set of equations where in this case, this pi sub 0 here, that's the zeroth entry in our vector pi. So this represents Osaka, or let's see which one was first, Kyoto. So that would represent Kyoto. So in this case, corresponding to the first column there, if we want to satisfy this equation up here, this steady state equation, then pi 0 has to equal 0 times pi 0 plus 1/4 pi 1 plus 1/4 pi 2, following this column here. Pi 1 has to equal 3/4 pi 0 plus 0 pi 1 plus 1/4 pi 2. And pi 2 would have to equal this 1/4 pi 0 plus 1/4 pi 1 plus 1/2 pi 2, just like the third column there. If these equations hold true, then the vector pi we're holding corresponds to the steady state of the system, or corresponds to the eigenvector of this. And we may also want to use the condition known as the normalization constraint, which says that since we're talking about probabilities, there's the probability that you were in some state has to total up to 100%. And so the probability, the sum P0 plus P1 plus P2 has to equal 1. Using all of these, if we actually solve for this, you'll find that pi 0 equals 1/5, and pi 1 equals 0.28, and pi 2 equals 0.52. So that vector of these three entries, 0.2, 0.28, 0.52, that would be an eigenvector of this particular system. So Hanako would be spending, on average, if you waited a month or 2 months or a year or something and asked, where is Hanako? There's a 20% chance you would find her in Kyoto, a 28% chance you would find her in Osaka, and or in Tokyo, and a 52% chance you would find her in Osaka. So this is what we call the steady state. We don't know where Hanako started. We don't know anything about her past history. All we know is she's been moving around among these three cities for some period of time in the past. And so there's some probability distribution that represents where she's likely to be. That probability distribution corresponds to the eigenvector for our system. And we can calculate it by hand this way, or we can calculate it using the other more sophisticated methods we've used for finding eigenvalues of matrices. All right, any questions? No questions? All right. I guess not. We'll go on. All right. That's the steady state behavior. That's the simplest thing to find here, because all you got to do is find the eigenvector of this matrix. But sometimes we actually want to know about the transient behavior of the system, which is what happens when the system is actually evolving over time. So we'll start with pi of 0 here being the time at where you started at time 0. Then pi 1 would be at time 1, pi 2 would be at time 2. And just like we had above, pi of n will be pi of n minus 1 times p. Or if you recursively do this, you'll find that this means that pi of n equals pi of 0 I should make this bigger. Pi of n equals pi of 0 times p to the n. Using this equation, then we can find the probability of being in particular states after n time steps. We can find that just starting from the initial state and knowing this matrix P, like our transition matrix up here. If we know that, then we can calculate this, and it's just like doing the steps that we saw earlier, including whether or not you actually graduate from the university, right? Let's see. Note that in this case, this transient behavior we were talking about here, this depends on the initial state. So pi to the n here equals pi 0 times p to the n. But up here, when we were calculating the steady state, we don't have anything about the initial state here. It doesn't matter. That's assuming that all you can get from any of the states in the system to any other state in the system. If you can't, then actually that initial state can actually affect this. In that case, it's actually not possible to actually find the steady state of the system because it probably doesn't have one. Well, depends. It may have multiple steady states that depend on where you actually initially started. All right. What does that? Where does that take us to? This was about discrete Markov chain processes. It's about the discrete time in this, where we were looking sometimes for the steady state behavior and sometimes for the transient behavior. But it's like staying in a city each night, and so nights are some discrete unit, and so that's what we worry about here. But time, of course, is continuous, so we can actually also talk about continuous time processes, which we might also call birth-death processes. That we can represent using a Markov chain that we would draw like this, where you start in state 0 and you have states 1, 2, and 3. This lambda and mu in the figure here represent the probability of the arrival of a customer, which we call birth, or the departure of a customer, which we call death. So these are called birth and death processes. And the number that's in the circle, or the state here, represents the number of customers who are in the system. So when the system starts, you have 0 customers in it, and when the first customer arrives, you have 1 customer in it. If the customer finishes and departs before a second customer arrives, then you would transition from the 1 state there back to the 0 state, and everything's quiet. But on the other hand, if a second customer arrives before you finish with the first one, then you would move from the state in the 1 circled state to the 2 circled state. So this represents then the number of people in your waiting room. If you're a doctor or a barber or whatever, and you're processing people, how many people? Well, not just the people in the waiting room, actually. Sorry, this also has to include the customer you're actually working on. So if you're a dentist or a doctor or somebody, this includes the patient you're currently seeing, plus all of the people in the waiting room. Now, obviously, this ought to be, if you think about it intuitively, if you have people arriving faster than you can deal with them, what happens? Well, that means that they're going to start accumulating in the waiting room, doesn't it? It means that as you process individual patients, that an average of more than 1 person arrives for each person you finish processing. If that's the case, then the number of people who are waiting in your waiting room is just going to continue to grow indefinitely. All right, let's see. What do we want to look at here? We can think of this as actually what we call flow from one state into another. Remember these lambda and mu here, they're rates. So this is how many per second or how many per hour or whatever your units are. And the question is, how can we calculate how many people are in the system? Well, again, maybe the one of the first things we want to deal with is we want to deal with steady state. So, of course, steady state in this case, we're not looking at exactly how many people are in the waiting room. There are exactly 17 people in the waiting room or 17 people in your system. What we want to know is, over a long period of time, on average, what's the probability distribution? What's the probability that when I go see when I go to your office, that I find N people in the system, that I find 7 people in the system, or 3 people in the system, or 1 people in the system. The probability for that, again, would be something that would be steady state. We can do this by treating each of these edges in the system as a flow and figuring out how much water or whatever is flowing from state to state is in each node, and we'll let that amount of stuff that's in our node represent the probability that we're in that node. So if you end up with all of your stuff, water or probability, in node 1, that means that then node 1 would have 1.0 in it and all the other nodes would be 0. That's pretty unlikely. If all of the first 100 nodes each had a probability of exactly 1%, then 0 to 100 would each have 0.01, and everything above 100 would have 0. That's also a pretty unlikely state. But, if you tried, you could create an artificial system that's like that. So one of the things we want to know, one of the ways we're going to deal with this is, first off, we're going to assume that each of these flows can be different from a different state. So this lambda 0 is the flow from state 0 to state 1. On this particular figure, it's not, they're all labeled lambda, they're just all equal. But in terms of our equations, we're going to write them as independent variables. Lambda 0 is the probability that we move out of that we move from 0 to 1, times the probability that that we were already in state 0. So the flow out of state 0 is lambda 0 p0. If we're talking about steady state, then what we want is for the let me see if I can draw on this. Annotate, draw like this. What we want is, we want to look at this boundary here, and what we want to know is, we want to find a state where the amount of stuff flowing left to right is exactly the same as the amount of stuff flowing right to left. So the way we calculate that then is this lambda for the state 0 times the probability that we're in the state 0 must be equal to mu for the state 1 times the probability that we are in the state 1. We can write that down as an equation exactly like this. lambda 0 p0 minus mu1 p1 equals 0, or mu1 p1 equals lambda 0 p0, or p1 equals lambda 0 over mu1 p0. You can write down the exact same set of things for each one of these boundaries. So in the case where where's my drawing tool? In the case where you want to go, where you're looking at the boundary between 1 and 2, and we want to know whether or not stuff going this way is the same as stuff going that way. Same thing. Oops. Same as the stuff going that way. Are these two equal? That's what we want to get. But so what I've just described here is actually looking at the flow across a boundary. That's going to be easier. So these equations 21 and 22 here are the right way to do things. Using these, you can actually solve the system, or solve for some basic things. And what we're going to look at is a particular type of Q known as the MM1 Q. This notation is developed by somebody named Kendall. If you've got this A/B/C, then A describes the arrival process, B describes the service process, and C is the number of servers you've got. So in this case, we have one server, and the arrival process and the service process are both this thing called M, which means memoryless, which means the same as a Poisson distribution, although we haven't talked about Poisson distributions. The way you read this is MM1, so it's an MM1 Q. And it's memoryless for both arrival and service processes, and it has exactly one server. In this case, all of those lambda sub I that I was talking about earlier, they're all actually equal. I'm not going to go through all of this process here. You can go through this and solve it. And if we set, let's see, where did I describe that here somewhere? Yeah. If you solve this, you'll find that the probability that you're in any particular state K is lambda over mu to the K times the probability that you're in that original state P0. All right, I think that's probably enough for this particular issue of queuing theory. At least for first-year undergrads, this is probably pretty advanced stuff for most of you all. But what I want you to understand is that using this set of tools, you can evaluate the probabilistically what the probability is that you're in a particular state in the system, and you can find what are called the steady state behavior of the system, as well as the transition states of the system. And you can calculate that using relatively simple math here. None of this is really super complicated stuff, even though it might seem like it a little bit at this point. Let's see. Anything else I've sort of missed here? It's actually useful to go and calculate all of these things. And in fact, if you want to calculate them, if you use a language known as Mathematica. Hopefully you can play with this using the code that's actually in the appendix here in the system, or in the set of notes. All right. That's everything about queuing theory that I have time to cover, really. Let me go back to my slides here for a couple of minutes. Where are we? Yeah, here. That was this. Check those out on the, I think if you actually spend a little bit of time with the notes, it'll actually make a fair amount of sense, even though they're fairly short. What's this related to? This might sound familiar. We actually did some of this kind of Markov systems last week in class when we actually calculated stuff using the PageRank algorithm in Google Colaboratory. So go back and check that out and think about it relative to what I've just told you in this particular case. All right, let me spend just a few minutes real quick. I don't want to spend too much time on this, but let's talk a little bit about error correction and then we'll wind up. I'm not going to have time to go through all of this in detail, what I would like, but I want you to understand the idea that, again, error correction is something that can be addressed using linear algebra. The example that's here is pretty much taken straight from the English Wikipedia page on what's called the Hamming code, the Hamming 7.4 code. It turns out that the material that's on that Wikipedia page actually makes a pretty good tutorial. So really, you should just go read it. That guy there on the right happens to be Richard Hamming. The only things you really need to know before we get started here is, let's see, remember parity is the sum modulo 2 of a set of bits. So parity of 0 and 0 is 0, parity of 0 and 1 equals parity of 1, 0 equals 1, and the parity of 1, 1 equals 2 mod 2, which equals 0. Before we go into that in detail, though, let's wind back and talk about a guy named Shannon, Claude Shannon, one of the most important scientists of the 20th century. This paper that he wrote in 1948 is considered one of the most important papers in scientific history. A mathematical theory of communication. If we go to Scholar, what do we get? A mathematical theory of communication has been cited. You will see that 146,000 times papers have cited Shannon's mathematical theory of communication. 146,000 research papers and books and other things have cited that. That's how important it is, right? That's a ridiculous number. So what Shannon realized, this is actually a diagram from the paper itself. You start with an information source that produces a message. That's on the left here. Over at the right, you have some destination that wants to receive that wants to get the message. The information source gives the message to what's called a transmitter, which creates a signal. The transmitter sends the signal to a thing called the receiver, which then conveys the message to the destination. But unfortunately, in the middle, there's this thing called noise between the transmitter and the receiver, which we can actually just model as a box we'll call the noise source. If we start with a system where you have two potential messages, or symbols in this case, we'll call them, Shannon drew this diagram for the first time, and it's a transition diagram showing that the upper one here we start here, then with some probability P, that the same message that was transmitted will be received. With some probability Q, instead, even though we started by transmitting this state up here, some damage happened to it, and we actually receive another symbol, not that one. Conversely, if you start down here with that same probability P, there is a probability that we went from the lower symbol to the upper symbol, and the same probability P that we went from the original symbol there on the lower part, and we actually was the transmitted symbol was the same as the received symbol. So in this case, maybe this is a 0, and maybe this is a 1. He's bigger, at least darker. That bigger. This one 0 and that one 1. So the probability then would be the same over here. The probability that we sent 0 and received 0, or the probability that we sent 1 and received 1. So on the this is an example in Shannon's notation of a channel that with some probability correctly transmits the message and with some probability doesn't correctly transmit the message. If we're talking about a single bit, our only two messages are 0 and 1, so I've labeled them here with 0 and 1, and you can see what the simplest example is like, but in Shannon's mind, it could be a larger alphabet of symbols. All right, clear all that and go back here. You can write this down as a transition matrix using the techniques we've just discussed. One of the things you need to think about, of course, is, well, P plus Q. P is the probability that it does the right thing, and Q is the probability that it does the wrong thing. So it always does either the right thing or the wrong thing. And so P plus Q must equal 1. Now, one of the things you should think about, what happens if you take your signal and or your transmitted message here and pass it through this channel a whole bunch of times, not just once, but a whole bunch of times. Be interesting. With that in hand, then we can talk about the Hamming 7.4 code. And again, this is just drawn straight from Wikipedia. What Hamming realized when thinking about the fact that punched cards that were used in the old style computer systems, thinking that those about how unreliable the data is from them, he realized that you can group the data together in ways and calculate a mathematical function on the data that allows you to improve the probability that the correct message is actually received at the receiver. The simplest way to do this, of course, would just be to repeat your message. So if the message is 0, instead of just sending 0 once, you send 0 3 times, 0 0 0. If the message is 1, you send 1 3 times, 1 1 1. That way, if an error happens on one of them, maybe the receiver gets 0 0 1, or maybe it gets 0 1 0. It can still figure out that the original intended message was 0 by doing just a majority vote on the set of bits it actually gets. That particular approach works, but it's actually kind of wasteful. It uses a lot of bandwidth because you're sending every message 3 times. Hamming was looking for something more efficient. This diagram here, you see 4 things labeled D1, D2, D3, and D4. Those are the original data bits that we want to send. So that's the original message. It's a 4-bit long message. Hamming realized that you can augment that 4-bit original message with 3 additional bits that we'll call the parity bits, or the error correcting bits. And if you calculate a parity of a subset of the subset of the original data bits for each of those parity bits, then that gives you the ability to actually detect and correct a single error in the system. That means when we want to send a 4-bit message, we're actually going to expand it out to 7 bits, and we send the 7 bits. So the data rate for this overall system is 4/7. So it's a little over 50% efficient, and that's a lot better than the 3 times for the system I was just describing a minute ago. This has, in error correcting terms, what we call a code distance of 3, meaning that there's a certain set of values for these bits that are legal values for it. And in order to get from one of those to any other one of those, you have to change actually 3 of the 7 bits. And we'll see why that's important later. Actually, we're probably not going to have time to go into that. Let's see. Now what? Well, as you might expect, there's actually some math involved in this. Hey, look at that. I see matrices. Looks like linear algebra, doesn't it? I think I can zoom here, can't I? Whoop, whoop, whoop. Maybe I can't actually zoom. I thought I could zoom in the zoom here. I thought I could zoom in using Zoom, but apparently I'm not sure how to zoom. So it goes. You see here on the right-hand side of the screen, unfortunately in rather small print here. Like I said, I encourage you to go read the page here. Usually I'm projecting this on a large screen in our lecture hall, and I'm actually writing on the whiteboard at the same time and working through examples. And so it does plus the students are looking at the slides online on their own laptops. So this particular case doesn't matter so much. But you'll see 2 matrices, one of which says is labeled G and one of which is labeled H. G is the generator matrix, and H is for actually for actually checking the parity of it in order to figure out whether or not an error actually occurred in the overall, or in the set of bits during the transmission. Yeah, I'm not going to have time to go through all of this because I actually need to kind of wind up for this, but I'll let you all go through this and see how taking your original data bits, your original message, and multiplying by the generator matrix gives you a message that's then robust against errors. When an error actually happens in it, then you can correct it using the check matrix. All right. With that, some final thoughts for the semester. This class in the SFC curriculum, again, let's see. Sorry, this figure's a little bit messed up. Assume that you all are all taking a Data Science 1 class here. This is 2 credits for that. In order to graduate from SFC, you have to have 1 Data Science 1 class and 1 Data Science 2 class at least. The other set of Data Science 1 classes include probability and statistics and basic calculus. The Data Science 2 classes include optimization theory and data science for healthcare, and about 7 or 8 different advanced options there, data science for business and things like that. I encourage you to take as many of both the Data Science 1 and Data Science 2 classes as you can. The classes are good, and they'll aid your overall understanding of mathematics and data science, and they'll help you with whichever career you actually wind up pursuing, whether it's economics or healthcare or quantum computing with me or whatever. Using the linear algebra at the SFC, there are a number of Keio, a number of the faculty seminars that you might want to that might actually take advantage of this. Notably, mine does in quantum computing. But if you join a Keio where you're studying deep learning or economics or bioinformatics or computer graphics, you're going to wind up using something like this linear algebra quite a bit. And in fact, some of the classes that will use linear algebra, Media Gijutsu, that's 3D programming taught by Professor Wakita, that uses linear algebra, and Kawashima Sensei's Saitekika no Suri, or optimization theory. Doesn't actually say that on there. It's optimization theory. And then also my class on quantum information processing, which is available in the fall. This fall 2023, I'll be teaching QIP in Japanese for the first time, but even if your Japanese isn't very good, you can still come join the class because we have all the materials available in English. It'll be fine. All right. Thinking again about the overall goals of the semester, I said by the end of the semester that students will be able to perform vector and matrix addition and multiplication. We covered that in lectures 2 to 4. All of you all did just fine with that. Solve systems of equations using Gaussian elimination, or Fangcheng is the Chinese term for it, that was for a similar system that was discovered a long time ago. We talked about linear and affine transformations, with the difference being with the affine transformations that they don't necessarily have to preserve the origin. And most importantly, we talked about eigenvectors and eigenvalues for small matrices, although the principles apply to large ones as well. That's really where I consider the core of this particular course to be. If you got to the point where you're comfortable with eigenvectors and eigenvalues, then you've got the main thing I wanted you to get out of this class. And then the last set of lectures here, where we've talked about things like graph theory. It might seem a little out in the weeds compared to straight up math that you've actually done before, but I think this kind of analysis of things like social graphs, you'll find, changes your thinking about systems in various ways. And so I think actually studying applications like graph theory actually turn out to be worthwhile. And then finally, of course, this being SFC, it's not just straight mathematics, but it's also about using information technology productively in your own life. And so we actually also spent some time doing Python code and a little bit of OpenSCAD for doing some basic linear algebra applications. And we did that for each of these different colored blocks here, including playing with the OpenSCAD stuff. So if you got as far as this, dealing with the eigenvectors and eigenvalues, again, you got what I wanted you to get out of the semester. And that's it for the semester. Thank you all for being here. Thank you for being my students, and come join my Kenkyukai, my research group on quantum information processing. And honjitsu wa shuryo shimashita. That's the today is done, or the restaurant's now closed. We will see you all at SFC, both in person and online. And good luck. Have a safe summer, and see you all in the fall. Bye, y'all.